to welcome Troy Day, who is the chair of mathematics and statistics and professor of mathematics and statistics at Queen's University. Troy did his bachelor's and master's at UBC. He then did his PhD at Queen's in the same department that he's in now. He did a postdoc he went back to UBC for a postdoc, then got his position, first faculty position at University of Toronto before coming back to Queen's, where he has been for several years now. He's a fellow of the Royal Society of Canada. He's interested in dynamical systems, game theory, optimization, etc. And today he will talk to us about the epidemiology and economics of physical distancing during infectious disease outbreaks. Over to you, Troy.
Thank you, Suresh, and thanks for the invitation to give a presentation to you guys. So as the title says here, I'm going to talk about some modeling we've been doing on the connection between epidemiology and economics during infectious disease outbreaks. This is joint work with David McAdams at Duke University, who's an economist there, and I'll mention him at the end as well. So to just kind of set the stage, I want to bring you guys back to the start of COVID-19, the pandemic. This isn't going to be about COVID per se, but it's sort of certainly motivated by COVID. This is a plot of, in the early stages of the outbreak, these are different countries, obviously. And this is a time series starting at the day when there were at least 20 active confirmed cases on a log scale. And so you can see exponential growth in all of these countries initially. And then, of course, there's this tapering off that's happened over time. And that tapering off is at least in part due to various non-pharmaceutical interventions that were put in place. And one of the ones that we were quite interested in and that I'm going to be talking about today is physical distancing. So basically staying home instead of going out and shopping or going to work or whatever the case may be. This is data on a more restricted geographic area. This is data from Ontario. It's cell phone data. This is March 2020. So again, at the beginning of the pandemic. And the way to read this is percentage check-in near home. So that's the amount of time that the person, or the cell phone at least, was near the home of that individual. And you can see these double dashed lines here are weekends. And so people tend to be at home on the weekends, then they go out during the week, then they're back at home during the weekends, then they go out during the week, and so on. And then there was this lockdown that was implemented, and you can see then people tended to stay home because all sorts of things in the economy were shut down. And one of the reasons for this, obviously, was to reduce the spread of COVID during that period of time. And to just indicate how effective that was, this is the same plot for this time series of activity level, basically. At this point in time is when the lockdown happened, and you can see that at that point in time, moving forward, there was much less activity. There's about a 2-week lag at that point, at least, between the reporting of a disease and when we thought that that individual actually got infected. So if you trace forward 2 weeks from here, 1, 2, you can see that's almost exactly the point in the epidemic curve where you see this break from exponential growth here to tapering off, so that this lockdown really had a significant effect in terms of curtailing the spread of the disease. And one of the things David and I were interested in is trying to understand people's motivations for staying at home or not, for physical distancing during the course of an infectious disease outbreak in general. And that's what I'm going to talk about, the modeling that we've done to try and explore that in a game theoretic context. So I say in a game theoretic context, the first thing I want to emphasize is that this notion of physical distancing is a game in a mathematical sense, in a technical sense. A game being a situation where the strategic interests of partners depend on what other individuals are doing. So my benefit to staying home will depend on whether others stay home or go to work, for example. And so physical distancing is a game both epidemiologically, because the consequences to me of whether I'm active or not depend on whether others are active or not, because that's where I'm going to potentially get infection from. It's also a game economically, in the sense that if others are out and the economy is open, that gives me a different incentive for myself to be out and participating in the economy or not. And so an individual's interests, both epidemiologically and economically, depend on what other individuals are doing. And so in that sense, it's a game. And when we want to understand individuals' incentives to either stay home or go out, we need to account for this interaction between individuals, these players in this game, if you like. What I'm going to present from this epidemiological model involves a few different, what I'll call canonical games. So very standard games from the game theoretic literature. So I want to quickly go through these just so that everybody's familiar if you haven't seen these before. So I'm going to start in this corner up here, the upper left corner. And these games that I'm going to talk about, you can think of as pairwise games. You and an opponent are playing. Really, what's going to happen in the epidemiological situation is you're going to be playing against the population at large. But here we can think of this as your choice. You can either go to work or you can stay home. And this is your opponent's choice. They can either stay home or go to work as well. And this first game I call a trivial game because it doesn't really matter what your opponent is doing. If I consider when my opponent stays home, it's better for me to go to work than to stay home because I get a payoff of 1 instead of 0. And likewise, if my opponent goes to work, it's again better for me to go to work because I get a payoff of 2 instead of 1. And so assuming the game is symmetric, meaning that my opponent is faced with the same strategic decision-making, there's a single, what we call a Nash equilibrium in this quadrant here, where we're both going to work. And it's a trivial game in the sense that I don't need to consider what my opponent is doing. And also, we're both better off here if we're at work than if we had both stayed home. Okay, so we both at that Nash equilibrium get a better payoff than we would if we were forced to stay home, for example. You can contrast that with this game in the lower right here, which is a prisoner's dilemma. So if I do the same kind of analysis here, if my opponent stays home, you can see it's better for me to go to work because my payoff is higher. And again, if my opponent goes to work, it's better for me to go to work because my payoff there is higher. And so again, there's a single Nash equilibrium where we both end up going to work. The difference between this game and the trivial game, though, is that we would have both done better if we had somehow been forced to stay home. Even though strategically each of us wants to cheat and go to work, we would both have been better off if some outside agent had forced us to both stay home. And so that's the sense in which there's a dilemma here. This is this prisoner's dilemma game. That's going to come up in the modeling that I'll talk about. The other two important canonical games are what I call a coordination game here, and it's just kind of what it sounds like. You basically get the best payoff by doing whatever your opponent is doing. If your opponent stays home, then you stay home. If your opponent goes to work, then you want to go to work. And so you end up with these two Nash equilibria, one there and one there. And their payoffs may differ, but the key point is that it's a coordination game. You both do best by mimicking one another's behavior, essentially. And that's, in some sense, the opposite of what I'll call a diversification game, where you get the best payoff by doing the opposite of whatever your opponent does. And so in this diversification game, the reason I'm calling it that is because there will tend to be a mixture of strategies in the population then. If your opponent is doing one thing, staying at home, then you have an incentive to go to work. And at some kind of Nash equilibrium, we're going to expect there to be some sort of mixture of behaviors in the population. So those are the 4 canonical games that I want you to keep in mind when I present some of the results from this epidemiological model. I should say, please interrupt me as I'm going along if something's not clear too. I'm happy to be interrupted and take questions throughout. So here's the general structure of the epidemiological model. That was a toy example with 2 players. Now I'm going to imagine there's a population of citizens, or we'll call them agents, that act individually in their own self-interest. And their decision is going to be whether they distance or not. So whether they stay home, which is distancing, or not. And we're going to suppose the population is very large in the sense that any single agent makes up a negligibly small component of that population. So a single individual's decision-making doesn't influence the overall dynamics of the epidemiological spread, for example, or the economic sort of background in which people are operating. And I'm also going to imagine that there's a government leader that can compel individuals to do certain things. They can compel coordinated action, like can compel people to stay home, or it could potentially compel people to go back to work as well. And I'm going to make the rather naive assumption that we were discussing just before I started the presentation here, that the government leader is going to act in the best interests of the population as a whole. So they're going to try and make a decision that makes everybody better off than they would have been otherwise. And sometimes that can be a decision that runs counter to individual self-interests, even though the population as a whole is going to do better under that decision. And then the questions I'm going to ask are really these. Is there well, how do individuals' incentives change over the course of an outbreak? So a disease comes in, spreads, it peaks, and then it goes out. How does an individual's incentive to distance change during that process? And are there any Nash equilibrium strategies? So a Nash equilibrium strategy is going to be a strategy as a function of time. You're going to be making a decision at each point in time throughout this outbreak. And the question is there a Nash equilibrium strategy over the course of an outbreak? And then, of course, what should a government leader do potentially in the context of this suite of personal incentives? So here's the structure of the model. It's going to be an epidemiological model coupled with an economic model. So I'll first explain the structure of the epidemiological model, and then I'll talk about how the economy interfaces with that. So the first key assumption is that each individual in the population can be in one of 5 different states. And actually, it's easier to see from the picture down here. An individual can be susceptible. They can be infected but asymptomatic. That's the C class. And that stands for carriage, like you're carrying the disease, but you're not actually, or you're carrying the infection, but you're not displaying disease. They could have recovered directly from there without ever having displayed symptoms. Or you can move from the asymptomatic class to the symptomatic infection class, and then you could potentially recover from there. And there's also a possibility of dying out of this class as well. So I'm going to use this calligraphic notation to denote the state that an individual might be in. And I'm going to use this notation here to denote the population density of individuals in each of those states. The other key assumption I'm going to make is that once you recover from the infection, you're immune to reinfection. So obviously this is not exactly like COVID, but it's not meant to be a COVID specific model. So we're going to suppose that you get complete immunity once you've been infected. I'm going to come back to this later, but also notice I have this box around these 3 states or these 3 classes here. This is a class of individuals who I'm going to call not yet sick, and they're going to be the focus of the analysis. I want to understand how these individuals should behave. And by not yet sick, I mean, if you're in any one of these 3 states, you have no way of knowing which state you're in. So if you've never displayed symptoms, you don't know if you're currently susceptible, if you're currently infected but asymptomatic, or if you've recovered from an asymptomatic infection. A key assumption underlying that is that there's not going to be any testing going on. So if I had testing, you would be able to discern whether I was in this state or this state, for example. But I'm going to suppose there's no testing. And so if you've never displayed symptoms, you know you're in that box, but you don't know which of those 3 states you're in. And it's going to be the behavior of individuals that are in this not yet sick class that's going to be the focus of the analysis. Okay, now, in any sort of analysis like this, the strategic analysis, I need to say what the decision variable is. What do people get to choose? And they're going to make a binary choice. They're either going to distance or not. So 0 means they're not distancing. 1 means they are distancing. This delta I is just the state that an individual is in. So their distancing strategy can depend on state. And of course, it'll depend on time as well as the outbreak unfolds. Alpha here is going to be a constant that denotes the effectiveness of distancing. So the larger the value of alpha, the more effective distancing is in the sense of reducing the contact among individuals. And I'm going to use this sort of paired notation, delta for an individual's strategy, it'll be 0 or 1, and D for the frequency of individuals using that strategy. So it's the expected value of delta. So it's the frequency of agents in class I at time t that are distancing. That's this Roman D. And just to tie this all together, this is what I mean by the reduction in the contact rate. So if you consider individuals in state I, and you want to know what's the overall contact rate of those individuals, well, that's a fraction di that are distancing, and so their contact rate is reduced by alpha, so it's 1 times 1 minus alpha, and then a fraction of the population is not distancing, and it's normalized to have a contact rate of 1. So this is the overall contact rate of individuals in class I at time t. Okay, now here's where I'm going to say a bit more about this box, this class of not yet sick individuals. So as I said, that's going to be the focus of the analysis. How should an individual who's not yet sick behave over the course of an outbreak? And when I say they're in the same information class, what I mean is there's no way for them to tell whether they're in state S, state C, or state RC. So they form a single information state, which I'm going to denote by this calligraphic N for not yet sick. And as a result of that, an individual's distancing strategy has to be the same if it's in, no matter which of these three categories it's in, because there's no way for them to know which of those three categories they're in. And so I'm going to refer to that simply as delta subscript N. That's the distancing strategy of a not yet sick individual. And it's going to be that thing that I want to understand. How should that change over the course of an outbreak? And for the other classes, the I class and the RI class, I'm going to assume that everybody in the I class distances. So the idea is either because they're symptomatic, they decide to stay home, or their symptoms are severe enough, at least, that they necessarily stay home. Either way, we're going to suppose that these individuals always distance. So their distancing strategy is set equal to 1, and we're not going to consider that in a strategic sense. And likewise, once you're in this class, you know you've been infected, you know you've recovered, and you know that you're immune. And so there's no incentive for you to distance any longer. And in fact, there's no reason why others would want you to distance either, because you're completely immune. And so the assumption is going to be that those individuals don't distance. And so there's no strategic analysis we need to make of that state either. So we're going to focus solely on the not yet sick class and ask, how should they behave over the course of an outbreak? So here's the set of equations. It's a standard, so the epidemiological equations. It's a standard sort of epidemiological model, a compartment model, if you're familiar with those. So this is the rate of change of the susceptibles, for example. This lambda function here is the force of infection. And so that's given by the transmission rate. So I didn't say this, but both of these classes can cause new infections. Everybody, when they're newly infected, goes into the asymptomatic class first, and maybe they never become symptomatic and they just recover, or maybe they become symptomatic. But both of these classes can generate new infections. So asymptomatic individuals can generate new infections, and symptomatic individuals could. And the results actually are going to depend in a very important way on which of those transmission pathways is most important. So the force of infection here has both of those terms: individuals that are in the C class generating infections, and individuals in the I class that are generating infections. And this is all mitigated by the activity level. So it's a simple kind of single outbreak model. Here's the carriage class. These guys can move at some constant per capita rate into the symptomatic class, or they can recover directly. That's these two pathways here. And then the symptomatic class, they can recover, and there's some possibility of dying from the symptomatic state as well. And the assumption is going to be that the population starts with basically nearly no infections, and an outbreak is going to take off, and we're going to analyze that situation. If all I cared about was the epidemiological dynamics, then that would be enough to describe what's going on. But remember, I want to know how does an individual's incentives change for distancing or not over the course of the outbreak. And so I need to understand how that particular individual state changes over time. It's not enough to know just what's happening in the population as a whole, but because thinking of myself in this not yet sick category, I might be progressing through the susceptible to asymptomatic to recovered state. I need to have some sense of how my state might change over time in a probabilistic way. And to do that, I need to build what is essentially a continuous time Markov chain to track an individual's state, because I want to consider what happens if this individual changes its behavior. What's its reward in the context of a population that's doing a particular thing? And so we have a system of equations governing the probabilities that an individual is in each of these 5 different states. Okay, and it's coupled to the epidemiological model because it's coupled through the force of infection, because an individual's state will change by them getting infected. And then once they're infected, their state changes in the same way as you've seen in the epidemiological model, these constant per capita rates. And so I've got this 5-state continuous time Markov chain that governs the state that an individual is in at any time. And in fact, really what you ought to do, and what I did do initially, is you can start with a population of individuals, each of which are obeying these dynamics probabilistically, and then scale up to a large population and end up with a deterministic system, which was this system here. But it's easier to explain the other way around, I think. So I have these pair of systems of equations that govern what's happening epidemiologically, and I'll just summarize them on this slide. So this is the population state variable, which I'll use X to denote. And here's the vector field for that system of equations. That's my population level epidemiological model. And then here's my continuous time Markov chain. So this Q matrix is the generator for this continuous time Markov chain. And it's coupled to the epidemiology. The epidemiology feeds into this discrete time, this continuous time Markov chain through this force of infection. So the generator depends on the force of infection, and as a result depends on the epidemiological dynamics. Okay, so that's the epidemiological setup for what's going on. The other thing I need to specify is what's happening economically. So in the analysis that I'm going to show you, people's decisions are made entirely on economic grounds. And by economic grounds, I mean certainly financial grounds would be part of that, but it needn't just be financial grounds. It could be any sort of utility that an individual gets out of activity, out of going out or staying home, for example. And so you can think of the economic stuff that I'm going to talk about now, both in terms of financial rewards, but also in terms of a broader sense of utility. So the way we're going to tie the economy into this model is we're going to suppose that there's a rate of economic flow to each individual at time t. So as an individual goes through its life, it's accruing some kind of economic reward as a function of time. And I'm going to suppose that it has this particular form here. So B is the rate of economic flow. It'll depend on an individual's distancing strategy, and it'll depend on something I called A here that I'll explain in a second. But the form is what's given here. I get some baseline reward no matter what I do. And then I have some reward for being active, which is this capital F. So 1 minus alpha delta I is how much activity is reduced as a result of me distancing. Remember, delta I is either 0 or 1. And so this FA is basically the reward for being active. And my reward for being active depends on A, which is the average activity level or average availability of others for interactions. And the idea here is that the economic reward that I get depends on whether others are out as well. I might prefer to go to a restaurant if others are going to a restaurant. I have a better chance of making money in my business, for example, if others are out and economically active. And so this reward for me going out depends on how many other people are out. And so A here, which is a function of time, is just the total number of not yet sick individuals weighted by their activity level. And then the total number of individuals who are symptomatically infected, and they're all distancing, so they have an activity level of 1 minus alpha. And then those individuals that have recovered from symptomatic infection, and they're not going to be distancing, and so we don't weight those, we weight those by 1. And so A is the availability or activity level of others in the population. We've tried to do a bit of a general analysis under some kind of reasonably general assumptions here, but what I'm going to talk about today is a more specific special case that's based on these assumptions here. I'm going to suppose that this function A is a linear function or an affine function. It's got a constant here, so I get some reward for going out regardless of whether others go out. But then I get some additional reward, A2 is positive here, for going out if others are also out, and that's proportional to how many other individuals are out. Okay, so this is this sort of positive feedback, if you like, synergy of reward for me being out when other people are also out.
So Troy, there's a quick question.
Yeah. Oh yeah, please
actually,
interrupt too, because I can't see the chat while
there are 2 questions actually. One asks whether does this equation always assume that distancing is detrimental to productivity? And the second question is, why is R underscore C of T not considered in A of T?
So it does assume that if I reduce it assumes that the value of going out is always positive, I guess, if that's probably the question that's being asked. So if I stay home, I get less of this positive reward than I would have otherwise. So there's always some benefit to going out economically. Epidemiologically is another question, but economically, that's right. The question about RC, it's in N here. So I wasn't clear about that. N is the sum of RC, of C, and of S. So there are three things that go into N. Good questions. Okay. Okay, so and now I need to, so I've got the epidemiological model, I've got the economic model, and I need to specify what people's objectives are. What do they actually trying to do when they're making their decision? What are they trying to optimize or maximize? And the assumption we're going to make is that they're trying to maximize the present value of their economic reward from that time onward into the future. And so to define that, I've got this function P here. This is the probability of going from, so this is an individual's probability of going from state J at time T to state I at time tau. Okay, because as an individual goes along in its life, it can change its state, and I need to know the probability of moving across these different possible states. I'm going to have a constant H, which is a typical kind of constant introduced in a lot of economic literature. That's a discounting factor, just to account for the fact that typically we weight rewards, present rewards, more than we'd weight future rewards. That might be because of financial reasons, because generally there's inflation, particularly now, for example. That's part of what would go into this discounting, but discounting might also include other things like I just care less about what happens in the future because maybe I'm not even going to be alive in the future. And so we have this generic constant H, which will just be a way of discounting future rewards relative to present rewards in a way that's going to be specific here when I talk about this integral. And so then we have this notation V sub I, which is the present value of all economic flow from time T onward for an individual that's in state I at time T. Okay, and that's what this integral is here. So there'll be 5 of these because there's one for each of the possible states that you could be in. They depend on the state of the epidemiological dynamics. They depend on the individual state as well. And it's the integral from time T onward, discounted by H, of the rate of economic flow. So B here is the rate of economic flow, which is varying over time for an individual that's in state K. And of course, an individual state, they start in state I, but an individual state can move from state I to state K with some probability all the way through time. And so this is the expected current value or present value of all economic flow from time T onward for an individual that's in state I. And then remember, the goal of the analysis is to try and understand what an individual in the not yet sick class is going to do at each point in time. And so if you want to write down what the present value for that individual is, well, it's the present value of being in the S class weighted by the conditional probability of being in S at time T. So that's the probability of being in state S divided by the probability of being in one of those 3 not yet sick classes, plus the present value of being in C times the conditional probability of being in C, and so forth. So that's the expected present value of a not yet sick individual at time T. And the assumption is they're going to try and make that as big as possible. Everybody in the population will be trying to make that as big as possible as time proceeds. Okay, so any questions before I go into the analysis?
Yeah, I actually had one question, and I'm sorry if I missed this, but is in the one set of questions was related to falling sick, and that's not in the currency of value, right? So is the cost of falling of being sick essentially coming from the reduction of activity to 0 during the period that you're sick, and the probability of dying and then getting your value completely down to 0?
Exactly. That is exactly what it is. I was just going to say exactly that. So the only cost to you becoming sick is that while you're sick, you may have a reduced economic reward because of your activity level. But also, if you're in this symptomatic class, there's some chance that you'll die, and then all future economic reward will cease.
Right. But so if you don't die, then the cost of staying at home is the same as the cost of falling sick, right?
That's right. That's right. So there is there's no cost that, you could imagine imposing a cost that's separate from all that. Just, I don't want to be sick and I'm going to weight it by this cost. And if I ever get sick, that's an extra cost that I incur. And that's not in here. The only cost that's in here is a cost that is something to do with a reduction in that economic reward in the future. And so that cost will depend on what happens in the future and what other individuals will do in the future. So it's quite a complicated cost, but that's the only cost that's in the model.
Yeah.
That's a great clarification. Thanks. Okay, so the typical way to analyze these kinds of problems is to work backwards in time. It's like a dynamic optimization problem, but it's a game. So it's a differential game essentially. And you want to, if you could sort of take time to infinity, then you could figure out, in a sense, this is a sort of very heuristic argument, what should I do in the infinite time limit? And now I can work my way backwards. Given I know what I'm going to do at time infinity, I can ask, what should I do a little bit before that? Because I know everybody will know what they're going to do at time infinity, and I can use that as sort of what to expect, given I make different decisions a little bit before that. And so you work your way backward in time in that sort of heuristic way, but you do it in a not heuristic way, to try and understand what the optimal or Nash equilibrium decision ought to be at each point in time during the outbreak. And the way you do that is typically with this Hamilton-Jacobi-Bellman. This is a system of partial differential equations, basically, that governs the reward structure over the course of the outbreak. So this is the instantaneous reward, if you like. That's that economic flow. These are vectors. So here it is here. This is that generator matrix, and V here is this vector of these different rewards. So this reflects the change in an individual's state and the consequences that has in terms of giving them different rewards as they plop into different states over the course of time. This is a factor that accounts for the fact that other individuals in the population are going to be doing something, and their decisions can have an influence on your reward as well, although you have no control over what they might be. So you can control this to some extent by your decision making. You can control this to some extent by your decision making. This is imposed on you by the decision making of others, essentially. And then there's a bit that's due to the fact that rewards are getting discounted over time as a result of this discounting factor H. Now, typically, that analysis that I mentioned, where you sort of work backwards in time, you break time then into sort of a current period of time, an infinitesimal slice of time, and then whatever happens from that point onward, assuming that you know what the decision making is going to be. Because if you're working backwards in time, you'll have already figured that out, essentially. And so when you do that, you can partition the equation into these three terms here, I guess. I'm going to focus only on the first two for most of what I'll talk about, but I'll explain everything here. So this is the instantaneous reward. So at time t, if I make a decision to distance or not, what happens? That'll affect my reward right now, but it'll also affect what happens to me in the future. And I know the optimal or Nash equilibrium decision-making of everybody in the future because I've worked backwards in time. And so I can use that to figure out, given all that, what should I do right now? And this has that form of a two-player game, but now I'm playing against the population. So my decision as a not yet sick individual against the background of the population. And so there's a baseline reward I get no matter what decision I make and no matter what other individuals are doing. And then there's a payoff I get for going out. That payoff is the economic reward for going out, which depends on this activity level of others. And then there's an epidemiological consequence for me going out. And let me just walk through what this is. QS, I think I've written it here somewhere. Yeah, here it is. It's the conditional probability of still being susceptible at time t. So this bit here is the probability that I'm still susceptible at time t times the force of infection at time t times the consequences, the cost of me getting infected at time t. And H here is just the difference in value of me being in the susceptible class versus being in the C class. So Suresh, to your question, that's exactly my cost of getting infected. It's the change in my economic reward of moving from state S to state C at time T. And so that's what this is. That's the epidemiological cost, in a sense, of going out. And so this is the total payoff for going out. And I'm weighting that by my activity level. If I distance, that'll be 1, and I get 1 minus alpha times that. If I don't distance, it'll be 0, and I get all of that. And so I want to distance if this thing is negative, and I want to not distance if that thing is positive, is the rationale here. And then this last bit is a bit you don't get to control, but it's others' actions on the epidemiological dynamics. And the reason I've included it here is because if I'm a government agent making a decision to make everybody stay home, well, that's not only going to change your reward here and change these things, but it will also change that. And so I need to account for that when I'm deciding whether or not, when a government official decides to make everybody stay home, what are the consequences to an individual? And that's a more complicated thing that I won't spend a lot of time talking about throughout the talk here, but I'm happy to discuss it in more detail later if people are interested. So I won't spend any more time on this. So there are these 4 games that I mentioned at the beginning. It turns out these 4 games play out in an interesting way during the course of an outbreak, and they play out in a different way depending on whether a disease is primarily transmitted asymptomatically or symptomatically. And so that's what I want to talk about for the results here. And so first, just a couple of, well, 3, I guess, kind of obvious results. So throughout, I'm going to assume that there's transmission by either asymptomatic individuals, that's these guys, or symptomatic individuals, that's those guys. And I'm going to suppose that the initial number of infections is small. Okay, and then there's these 3 lemmas that are not hard to prove, and they're kind of obvious. The first is that the outbreak is transient. By the structure of the equations, there's no inflow of new susceptible individuals. And so if an outbreak occurs, it's going to go up and it's going to come down and it'll be over. It's not surprising, and it's not hard to prove that. So C goes to 0 and I goes to 0 in the limit, regardless of what individuals do in the population. That will eventually happen. Another thing that's maybe not so obvious, or maybe not so surprising as well, is that nobody should distance before or after the outbreak. So when the number of infections is really, really small beforehand, everybody's out doing their thing. There's no incentive to be distancing. And likewise, once the outbreak has run its course, everybody should be out and not distancing and doing their things. And so it's not hard to prove that that's true. And the limit as T goes to 0 and T goes to infinity, then Nash equilibrium is a trivial game where nobody's distancing. And then the last thing, which again, also is probably not so surprising, if the outbreak is severe enough, meaning that the case number goes up enough and the consequences of being infected are severe enough, then there'll be a point in the middle of the outbreak where there's a trivial game where everybody is distancing. So it's a trivial game where no matter what other individuals are doing, you're better off staying home. And again, that's not terribly surprising, I think. And so the general picture looks something like this in the case where there's a severe enough outbreak. You have a phase. So here's the force of infection, also the number of individuals infected, if you like. That's that it goes up, it goes down, and its limits are 0 on either end. Nash equilibrium is to not distance before anything happens and to not distance afterwards. And in the middle, if it's bad enough, there's a trivial game where everybody's distancing. And so the only real question is what happens in the shoulders there and there? What are the strategic interests of individuals as we're just coming into a really severe outbreak and just leaving a really severe outbreak? And that's where it depends on whether or not transmission is symptomatic or asymptomatic. So I'm first going to give you the results for asymptomatic transmission. And I'll just state what they are. In an asymptomatic transmission case, there's a diversification game that happens just before the severe part and just after the severe part. So you come in and there's this diversification game where if lots of people are distancing, you don't want to, and vice versa. And that results in a mixture of distancing strategies. And as the outbreak gets more and more severe, then eventually everybody distances, and then you come out the other end in the same way you went into it. I'll say a bit about this if we have time. It turns out that there's an interesting prisoner's dilemma that happens just before that diversification game. and just after that diversification game as well. But we'll come to that later if there's time. So the general picture looks like this. You got this no distancing Nash here, and here you've got everybody distancing there because it's a trivial game. And then as you proceed, ignore the red down here, as you proceed through, you get an increasing fraction of individuals distancing till you hit 100% if it's severe enough, and then you go out the way you came in. And so the Nash equilibrium has that mixed flavor as you go through the outbreak curve. What's interesting is here in that little window, there's a prisoner's dilemma in the sense that individuals have no incentive to distance. But if a government official was to force everybody to stay home and distance, everybody would be better off than if they hadn't, and if they'd acted in their own self-interest. So you'd still have an incentive to cheat and go out when everybody else is staying home, but forcing everybody to stay home in this little window turns out to do everybody better than if you let them act in their own self-interest. It's a sort of tragedy of the commons in a sense. So there's a little prisoner's dilemma window there. On the other hand, if the transmission is symptomatic, then you get a coordination game that happens before the severe phase and after, as you come out of the severe phase. And again, you can get a prisoner's dilemma on either end of that, but now the prisoner's dilemma is one where the government official would try and force everybody to go to work rather than stay home. So the picture looks like this. You have this no distancing Nash here and here on the end. You've got everybody distancing in the middle when it's very severe. And as you pass into that, you get this period where there's this bistability. So there's a coordination game where if everybody's distancing here, then you'd want to distance. But if nobody's distancing there, then you would also not want to distance. And so there's the Nash equilibrium is not unique. You have this bistability in a sense as you move in here. And then eventually you hit a phase where there's only one Nash equilibrium, which is this game where everybody is distancing. And then you have the same thing on the way out the other side. And here's where you have that little window of a prisoner's dilemma on either end. Only now everybody has an incentive to distance, but they would have been better off if everybody had been forced to go out and go to work instead of distancing. So they would have been better off if someone forced them to act against their self-interests here. Nevertheless, there'd be an incentive to cheat still. You'd try and cheat and stay home despite the fact that you're being forced to go to work. What I want to do is try to explain, give you some intuition for why those results are the way they are. And I'm going to focus first on the asymptomatic case, which is what's on the left-hand side here. So remember, this is the force of infection. So in the asymptomatic case, it's only the asymptomatic individuals that are transmitting the infection. Everybody, you can display symptoms, but it's only the asymptomatic individuals that are transmitting the infection. And if I'm trying to understand an individual's strategic decision-making, what I need to understand is how this activity payoff changes over time. Because if that's positive, as an individual, I want to go out. And if that's negative, I want to stay home and distance. And so to try and understand those results, what's important is understanding how that activity payoff changes as collective distancing is enforced. So how does this payoff change if everybody was forced to be distancing or not? How does my reward for going out change if a government official forced everybody to stay home, for example? And there are two parts to that. There's this economic flow and there's this epidemiological reward. So if a government official forced everybody to distance, to stay home, I lose out in my economic reward because there's some benefit for me going out if others are also out. That's that positive reward for others being active when I'm active. But there's also an epidemiological consequence for that. If a government official forces everybody to stay home, then my payoff for going out is higher because I'm less likely to get infected. And so those things work in opposition to one another. Forcing people to stay home makes me less inclined to go out because there's not as much economic reward for me going out, but also I have less risk for going out. And so there's a tension between those. And it turns out that the tension is always won by the epidemiological piece. Because there's some reward I get economically, regardless of whether I go out or not. Whereas the epidemiological consequences are mediated entirely by the activity levels of other individuals. And so that means that as other individuals are forced to distance, my payoff for going out goes up. The reduction in the risk is more than enough to compensate for the loss in economic reward as individuals are forced to stay home. Okay, and that's what you need to understand what's happening in the asymptomatic case. So if you force other individuals to stay home, your activity payoff goes out. That introduces this flavor of a diversification game. The more other individuals stay home, the more your incentive is to go out because of the reduced risk. And that's why you get this diversification game happening in the asymptomatic case. If you contrast that with the symptomatic case, which is what's on the right here, now remember we're asking questions about the behavior of a not yet sick individual, and those individuals are not doing the disease transmission now. It's the symptomatic individuals that are transmitting the disease. So again, I ask that same question though, how does collective distancing affect the activity payoff? If everybody else is forced to stay home, how does that affect my reward for going out? Again, there's an economic bit. If everybody's forced to stay home, my reward economically for going out is reduced because of this positive component to the reward. But the epidemiological piece is unaffected by that because it's not those asymptomatic individuals who are doing the transmitting. It's the symptomatic individuals. And so collective distancing always decreases the activity payoff. The more others are forced to stay home, the less reward there is for me to go out, and that imposes this kind of flavor of a coordination game. I tend to do what others are doing. If there's lots of individuals out, I'd like to go out. If they stay home, there's no reason for me to not stay home also. And that introduces this flavor of a coordination game here. Maybe I'll leave it at that. I'm happy to talk about the prisoner's dilemma part of this as well, but yeah, maybe just briefly I'll say for the prisoner's dilemma, the easiest thing to understand is what happens if we look at the asymptomatic case. What happens right before this threshold where the activity payoff is zero? Remember, when the activity payoff's positive, I want to be out. When it's negative, I want to stay home. At zero, I'm indifferent. So just before it becomes negative, just before things are bad enough to make me want to stay home, you can ask what happens if everybody was forced to stay home. So right in this little window right here, if everybody was forced to stay home, that increases the activity payoff. It increases the value for me going out. And if you force everybody to stay home, that makes this bigger. Of course, I get a little bit of reduction because I have to stay home now, but overall, my payoff is bigger than if I had just been left to my own devices and I'd actually stayed out here for that period of time. Because the reward for forcing everybody to stay home is more, but I only get that reward if everybody else is doing it. And that's the tragedy of the commons. You need some external agent to somehow coordinate that behavior. Otherwise, everybody's going to act in their own self-interests, which will be individually to cheat and to go out, despite the fact that if everybody agreed with one another that they should all stay home, they would all have been better off. Okay, and a similar sort of thing is happening in that window, except it's the mirror image of that, where now you're better off being forced to go out rather than stay home. So I'm just going to summarize there, and then I'll be happy to take questions. So as I said, I don't want this to be about COVID per se, but in the back of our heads, we had sort of this rough dichotomy in mind between COVID-19 and SARS, which had a minor outbreak in 2001. So with with COVID-19, that was a large amount of transmission was happening asymptomatically. And so in terms of this dichotomy, it was more along the lines of this case here, where you have this diversification game happening than it would have been more along those lines than a coordination game. But in SARS, which happened in 2001, almost all of the transmission happened symptomatically. People didn't transmit the disease when they were asymptomatic. It was only when they're displaying real symptoms, and often in hospital actually, that the transmission happened. And so that would place it more along this sort of lines. And as a result, it would generate more of these kinds of coordinated action dynamics than it would the diversification game. But I'll stop there, and I'm happy to take questions and comments. Thank you.
Thank you very much. So if you have questions, you can put them in the chat, or you can raise your hand, though I don't always see them. So yeah, are there any questions? Yeah, because I have two, I can start it off if nobody has any questions. Yeah, I mean, of course, I'm sure you get these questions where people ask you to consider different situations of interest, right? So for me, the two situations I was considering was, so for you, distancing was essentially all or none. So you stay at home and your activity is zero. I was really curious about the situation where you can go out and obey the rules that supposedly bring you to a state of reduced transmission. And then the role of social trust, as in whether you trust that everyone will will obey the rules, which would give you a higher level of activity, perhaps even a value close enough to being normally active. And yet it relies upon everyone obeying the rules, right? And this is where you bring in the interesting situations of Sweden versus social trust and belief and all these concepts. I was wondering if you had considered this intermediate state of distancing where
Yeah, that's a good question. So, I mean, not explicitly, but we sort of thought of that as being mediated by this parameter alpha. So if alpha is something that's, say a half, then whatever that we're calling distancing, whatever that behavior is, it reduces your activity level only by a half. And so that could be something like wearing masks, or maybe even more extreme, it reduces it only by a small amount. You can still do the same analysis then where my distancing choice is 0 or 1, but the consequences of distancing are less significant in terms of reducing the contact rate.
I see, but that's where it gets really interesting is not only you're wearing the mask, but how many people are wearing masks, right? So that alpha may be could be more diverse in the sense that it could be multiple. I'm just thinking aloud here.
Yeah, so yeah, I guess we haven't done this, but you could have a model where I have activity level, and then I have another decision, which is how much precaution I take while I'm active or something like that.
Yeah,
and you could do both of those at the same time. The way I was describing this, I was more thinking that, let's suppose everybody's out, and delta equals 1 means I'm wearing a mask, and delta equals 0 means I'm not wearing a mask. And so it's no longer a stay home, go out sort of decision, but a masking or not decision.
Right. But if we believe the idea that masks are to protect others, not to protect yourself, then it's this interesting question of your perception of how many people are wearing masks matters, right? When you go out.
Well, that, and you're right. If it's mostly protecting others, then that changes the incentive structure a lot too, for sure.
Yeah, the other thing I had in mind was it was interesting that you had the infected stay at home, even though it isn't their incentive to go out. The only, because it's kind of a forced setting, right? Because for them, all the incentive tells them individual self-incentive is to go out. That is, of course, it's fine. But I was wondering whether there is some curious paradoxical situation where a small number of infected people going out can change the behavior of everyone else, because they are kind of adding a high, essentially it's not probabilistic anymore. They are guaranteed to transmit, let's say, for example. And so essentially a very small number of infected people breaking the rules can force everybody into staying at home because they're scared of these infected people.
Yeah, that's right. So one thing we started out doing to try and account for that a little bit is, let me go back a little bit here to explain. So it's just the place I want to be. Yeah. So, well, maybe actually a little further back. We assumed here that there's, in this not yet sick class, there's a reduction by alpha of your contact rate. And we assumed that if you stayed home, or sorry, if you stay home, oh yeah, that's right. It is 1 minus alpha. That's what we did. We did an analysis where the alpha here is different from the alpha for I. So if I'm a not yet sick individual and I decide to stay home, that reduces my contact level. I still assume all the infected and symptomatic individuals stay home, but by them staying home, it's not necessarily the same reduction as it is for the other classes. And so you could incorporate a kind of leakiness like you're talking about there, where maybe then they're not staying at home as much as you'd think they would be. It became, I can't remember off the top of my head, there was some problem with the analysis where it was hard to figure out what was actually going to happen. So it did make a difference. And we couldn't quite sort out exactly anything definitive to say in that case, is my recollection. So that's an interesting observation for sure.
Yeah, as I think you already got it, but I was kind of really curious about this apparently paradoxical situation where a small number of rule breakers can improve the situation for everybody in a certain sense.
Yeah, no, absolutely. That's the other thing we started out doing, which makes a big difference, is testing. So then you can, if you've been tested, you know which one of these classes you're in initially, immediately after the test at least, but then you start to lose information as time goes by because you're no longer certain that you haven't been infected since your last test. And so you can set the whole thing up as a system of equations where you're tracking the time since tested in these categories as well, which is quite interesting, but that became a little bit more than we could manage at the time.
Is there any simulation code available that people can play with?
Not available yet, but when we publish this, we'll make something available. I've been having a hard time. So it's easy to simulate the outbreak and simulate given a set of assumptions about how individuals behave. That's all obviously not hard to do. It's quite hard to numerically compute what the Nash equilibria is, though, because it's hard to do this backward calculation numerically. In certain settings, like in the ones I talked about here, you can prove that certain properties hold, but it's quite hard to actually compute a numerical instance of this.
I see. That's also why you don't have data comparisons or anything with any particular outbreak.
Yeah,
Okay.
yeah. Well, that, and I mean, this is a very, very heuristic toy model as well, for sure.
Any questions? I definitely don't want to be taking up all the time. Anyone? So I guess I'll ask one more question, which is, you know, when you this is more of a general question. So when you take up a model like this in a heuristic sense, is it the idea that you hope to find some general principles that then apply not even in general to compartment models of this kind?
Yeah, I mean, it's a risky business, obviously, but that's exactly what the idea is to, I mean, if all I had done in a model like this was, say, generate, well, I didn't show you any curves plots, but if I was to generate this prediction, say, and I could show you what the curves look like, and you know, people stay at home and there's a prisoner's dilemma here. If all I did was tell you those results, it would be much less satisfying to me. What I really want to do is this part. I want to understand why the results are the way they are, and by having a very simple model, I can actually dig into it well enough that I can understand what's happening. And then the idea is hopefully that understanding I can take, and I'd never want to apply this model to any real world situation, but I can take the understanding I've learned from this toy model, and it'll help me to think about what might happen in a more realistic scenario. That's kind of the idea, but obviously that's so we are sometimes essentially works, sometimes doesn't.
So this is the great statistical discussion about explainability versus applicability of modeling, right?
Absolutely. And if I cared to make a prediction about, you know, what happened in Ontario, it would not be this model. But if I want to understand the factors at play in a sort of generic sense, that's the point with something like this. Another thing that's missing here, one of many things that's missing here that I think is really important and interesting, is everybody here has the same economic incentives, in the sense that, you know, there's no difference in job sectors or anything like that, right? And so obviously that was not the case during COVID. Some people had to go to work because they didn't have the luxury of not going to work. I could stay home and do what I do from my home. And so the consequences and the incentives were very different for different segments of the population. And that's going to have an important role as well. That's completely absent from this.
Yeah, it will be really interesting if that particular point you raise, which also includes the people making the rules for others, being in class 1 or class 2. But it could be a very similar model, but with the interpretations being completely different, right? And that's a sort of, it would be interesting if the parameters are literally transferred from one situation to another, but then the interpretation is quite different.
Yeah, for sure.
Cool. Any other questions? Last chance, last call. Okay, if there are no other questions, it's a fascinating talk. Thanks a lot. And thanks everybody for coming. So
Thank you,
Alex,
Troy.
you start the recording?
Yep.